Boa tarde, pessoal. Sejam bem-vindos, então, ao nosso segundo bloco desse terceiro dia do primeiro simpósio sobre plásticos reciclados no asfalto. Nesse segundo bloco, então, vamos ter a engenheira, a doutora engenheira Silvia Angelone, uma grande amiga aí da Argentina. Vou apresentá-la, então. Ela é especialista em engenharia de pavimentos, engenheira civil, mestre em engenharia rodoviária e doutora em engenharia pela Universidade Nacional de Rosário. Ela trabalha como professora associada e pesquisadora na Universidade Nacional de Rosário, é professora de pós-graduação em diversas universidades da Argentina e diretora do mestrado em engenharia rodoviária pela mesma universidade. Atua também como pesquisadora, assessora e consultora no Laboratório de Estradas do Instituto de Mecânica e Estruturas Aplicadas, IMAE, nas áreas de engenharia de pavimentos, mecânica de estradas, solos, materiais rodoviários, projetos de pavimentos e sustentabilidade rodoviária. Dirigiu e dirige vários projetos de pesquisa e desenvolvimento e acordos de transferência e cooperação, e ele é autor de vários artigos em revistas e livros de conferências dedicados à engenharia de pavimentos. Bueno, Silvia, una vez más, un gusto estar con vos aquí. Gracias por aceptar nuestra invitación. Bueno, dejo entonces la palabra con vos para que puedas compartir con todos los amigos de Brasil y del mundo el proyecto PASOS. ¿Ok?
Muchas gracias, Rafael. Muchas gracias a todos los organizadores de este evento. Y trataré de explicarles nuestra experiencia. Voy a compartir la pantalla, así se ve la presentación. Ahí se ve bien. Bueno, hemos tenido grandes expositores previamente. Hay un montón de conceptos que por suerte entonces ya han estado presentes. Y lo que voy a hacer ahora es contarles una experiencia que hemos hecho en Argentina, que lo denominamos Proyecto PASOS por Pavimentos Sostenibles, y vamos a ver cuál fue la experiencia en un tramo experimental con plásticos reciclados. Lo primero de todo, porque no todo el mundo sabe dónde queda Rosario. Rosario está dentro de la provincia de Santa Fe. Es una ciudad que no es muy grande, de alrededor de 2 millones de habitantes. Y lo que tiene de interesante y que hay que recalcar es que está en una zona agroexportadora. ¿Qué significa esto? Que casi todas las rutas que llegan a Rosario llegan para descargar en los puertos cerealeros. Por tanto, todas las cargas son muy pesadas. ¿En qué va a consistir la presentación? Va a consistir en una introducción, en ver el objetivo, cuál es la metodología que usamos para incorporar los plásticos reciclados, ejecución y seguimiento de los tramos y conclusiones. Cuando hablamos de sostenibilidad o sustentabilidad en carreteras, hablamos de conservar, de gestionar la infraestructura del transporte. Para ello, vamos a querer diseñar para durar más tiempo, para maximizar el reciclado, para minimizar los impactos sobre el medio ambiente. ¿Qué buscamos? Soluciones inteligentes para atender una infraestructura de transporte sustentable. Introducir la sustentabilidad para cambiar la visión de la infraestructura de transporte. Un enfoque más multidisciplinario para introducir nuevas tecnologías. El proyecto PASOS, Pavimentos Sostenibles, es un camino a la sustentabilidad. Queremos valorizar residuos y uso de residuos en la carretera. ¿Qué buscamos? Alternativas sustentables, reciclado y reutilización de residuos, uso y disposición responsable de residuos, reducción de consumo de energía. pero siempre teniendo en cuenta que la carretera no es un vertedero. La incorporación de residuos no debe reducir su calidad ni su comportamiento. Si utilizan residuos, se igualan o mejoran la calidad de los materiales viales que forman parte de la carretera. Cuando hablamos de un residuo, ¿todo residuo se puede reciclar? No. Para que se pueda reciclar tenemos que tener el residuo, la disponibilidad, la viabilidad técnica y económica. Y ahí se convierte en un reciclado. Desde la universidad, desde lo que investigamos, generalmente miramos primero la viabilidad técnica. La viabilidad económica la va a dar el mercado. Nosotros hemos venido en la Universidad Nacional de Rosario, en el laboratorio vial, estudiando diferentes materiales, no únicamente plásticos. Hemos trabajado con RAP, con residuos de la construcción y demolición, digamos, principalmente residuos de hormigón, neumáticos fuera de uso, y ahora estamos en plásticos. También se usaron escorias siderúrgicas y otros residuos industriales. ¿Por qué plástico? ¿Por qué plástico? Porque hay mucho. Solamente de los residuos sólidos urbanos, el 13% forma parte de esa basura, de ese waste que hay. Entonces, de los plásticos tenemos prácticamente 1 millón de toneladas al año y solo se recicla el 12%, alrededor de 200.000 toneladas al año. Entonces, hay un montón de plásticos, a esto tenemos que agregarles los plásticos industriales, que debemos darle algún destino. Entonces, se sabe, ya lo escuchamos a los participantes anteriores, que desde el año 2000 y antes inclusive hay una extensa investigación y la mayor parte es por vía húmeda. En los 4 continentes ha habido experiencias e investigaciones sobre este tema. Por vía seca son menos las experiencias y las experiencias in situ son más limitadas todavía. La India, España, Holanda son algunos de los ejemplos de uso in situ de las mezclas asfálticas con plástico. ¿Cuáles son los objetivos del proyecto PASOS? Contribuir a la mejora del medio ambiente, usar plásticos reciclados, construir tramos experimentales con mezclas asfálticas elaboradas con plásticos reciclados, verificar in situ si se cumplen las ventajas observadas en los estudios de laboratorio, realizar una efectiva vinculación y transferencia entre las empresas privadas, públicas y la universidad. Esto se logró. ¿Por qué? Porque a partir de la universidad, uniéndonos con la empresa petrolera, desde el año 2012 venimos estudiando diferentes plásticos incorporados por vía húmeda y por vía seca en las mezclas asfálticas. Lo que no teníamos hasta principios de 2018 era una empresa que nos diera una cantidad suficiente de plástico reciclado. Encontramos la Asociación de Cooperativas Argentinas, que es una asociación de productores agropecuarios que empezaron a reciclar plásticos provenientes de silobolsas y envases fitosanitarios, bidones, que ya veremos qué son los silobolsas. Conseguimos la colaboración de una agencia vial, que es la que comanda toda la provincia de Santa Fe, y la concesionaria que nos permitió en sus tramos hacer la experiencia. Mucha gente que estuvo involucrada, excelente predisposición, colaboración de todos, y aparte cada una de las partes integrantes puso aportes económicos importantes para llevar a cabo esta experiencia. Como les decía antes, nosotros venimos estudiando desde el año 2012 distintos tipos de plásticos, polietilenos de baja densidad, de alta densidad, en forma de escamas, o pedacitos, como lo mencionaba antes Lili, o en pellets. También usamos polietileno micronizado, también trabajamos con el polipropileno y con el PET. Desde ya les digo que el polipropileno y el PET no nos dieron los mismos resultados, y hay papers anteriores, que lo que es el polietileno. O sea, para nosotros el polietileno tiene más ventajas o mejor comportamiento. Entonces estudiamos ahora en los tramos experimentales los polietilenos de baja densidad, de alta densidad y en forma de pellets. Les había dicho que venía mucho de este plástico reciclado de los silobolsas. Los silobolsas son grandes bolsas que almacenan granos. O sea, tienen alrededor de 3 metros de diámetro y entre 60 y 70 metros de longitud. Cada uno almacena alrededor de 250 toneladas de granos. Y tienen 3 capas de polietileno. Una de baja densidad blanca por fuera y las otras 2 son de alta densidad y con incorporación de negro de humo, por eso es negra la interior. Tienen una vida útil de alrededor de 2 años y queda un residuo. Entonces, la Asociación de Cooperativas Argentinas puso una gran planta de reciclado alemana de última tecnología que recicla 7.000 toneladas anuales. ¿Y de dónde provienen? De silobolsas, que nos va a dar polietileno de baja densidad, y de bidones, que nos van a dar polietileno de alta densidad. La planta de por sí tiene una economía circular. O sea, ellos casi el 100% en este momento de lo que están reciclado va, o el 90%, a volverse a incorporar a silobolsas o a bidones. Parte de ello va a ser sacos, bolsas para supermercados o para uso urbano. Y nosotros estamos proponiendo usar en carreteras. Lo usamos por las 2 vías, por vía húmeda y vía seca. ¿Cómo hicimos la vía húmeda? Usamos un asfalto base blando, denominado SPRA2020. Le agregamos los pellets de baja densidad o de alta densidad a 170 grados y se lo agitó hasta que quedaba incorporado. Y una vez que ese asfalto estaba modificado, después se puso en la mezcla asfáltica. La cantidad que usamos fue 3% respecto al bitumen. Por vía seca, primero se mezcla el agregado con el mismo asfalto que usamos de base y después se le incorpora una mezcla de filler más pellet. El filler usado fue cal. En este caso, la cantidad que se usó fue el 2% respecto a las mezclas. Ambos porcentajes son conservadores. Nosotros hemos hecho estudios en los cuales llegamos por vía húmeda hasta el 6-7% y por vía seca llegamos hasta el 5%. Estos 2 porcentajes son conservadores, se incorporan muy bien tanto al bitumen como a la mezcla asfáltica. Veamos qué cantidad de plástico genera esto. Más o menos para 1 kilómetro de camino, si consideramos que una bolsa pesa 6 gramos, por vía húmeda se emplea aproximadamente 1.300 kilos, son 200.000 bolsitas, y si fuera por vía seca llegamos a 18 toneladas, 3 millones de bolsas. ¿Cómo se diseñaron los tramos? Los tramos se construyeron a fines de 2018, o sea, ya casi estábamos en el verano, y consistían en 5 tramos. Un tramo de control con un asfalto CA30, que es el que se estaba usando. Después se hizo un tramo con bidones por vía húmeda, bidones por vía seca, silobolsa por vía húmeda, silobolsa por vía seca. La mano esta, que tiene todos los tramos, es la más pesada, la que va con mayor tránsito, la que va hacia la ciudad de Rosario. Y la otra mano, los 500 metros de este otro lado, se hicieron todas con silo bolsa por vía húmeda. Cabe destacar que nosotros no hemos cambiado nada el diseño que tenía originalmente la empresa, sino que lo que cambiamos fue la cantidad, digamos, el tipo de bitumen que estábamos poniendo. La planta es una planta chica por pastones, tenía un molino a pie de planta para poder modificar el asfalto, terminadora, y teníamos compactadores que después vimos que eran insuficientes, como lo dijeron anteriormente. ¿Cómo se hizo por vía húmeda? Acá tenemos el molino de 2 toneladas, se le ponía el asfalto base, se le agregaba el plástico en pellets, se lo mezclaba a 170 grados con una mezcla, no era una agitación muy grande, y una vez modificado era totalmente bombeable, no teníamos problema de incorporarlo directamente en la planta de mezclas asfálticas. Se tomaban muestras y se hacían los resultados. Entonces, como no sabíamos qué tiempo de agitación le teníamos que dar, lo primero que hicimos íbamos sacando, digamos, primero lo hicimos a la media hora, a la hora, y así íbamos viendo si estaba totalmente homogéneo o si se veían los pellets. Seguíamos agitando hasta que quedaba totalmente uniforme y homogeneizado. Esto llevó a que el polietileno de baja densidad llevara 2 horas y media de agitación y el de alta densidad llevara 4 horas. Cuando elaboramos por vía seca, se hizo primero la mezcla del agregado pétreo con el asfalto, y la mezcla del filler con el plástico se puso en la tolva del filler, que se incorpora al final. No se le dio más tiempo de mezclado que se le da habitualmente. La mezcla se elaboró a alrededor de 170 grados y estaba totalmente envuelto, totalmente incorporado el plástico a la mezcla. Y así se llevaba a in situ, donde se pudo distribuir bien, se pudo compactar. Acá tenemos que ver, empezamos a ver algunas precisiones de la experiencia que hicimos. Es muy importante la temperatura, o sea, es importante que no se enfríe, o sea, mantener esa temperatura. Una de las cosas que no logramos es que nosotros queríamos espesores entre 40 y 50 milímetros y no lo logramos, se lograron espesores más bajos, con lo cual la mezcla se enfriaba rápidamente. El primer tramo que se hizo fue con silo bolsa por vía seca. Tenían la gente muchas dudas y entonces la última parte del tramo quedó frío y entonces eso hizo que la compactación no fuera tan efectiva. Lo que veíamos cuando pusimos la mezcla por vía seca es que tomando la mezcla de la terminadora, uno podía observar hilos del plástico dentro de la mezcla. O sea que en sí no está totalmente fundido, sino que está incorporado dentro de la mezcla, pero no se veían los pellets. Lo que se veían eran estos hilos. Vamos a ver entonces ahora los ensayos. Dijimos que habíamos hecho silo bolsa, que es de baja densidad, bidones, que es polietileno de alta densidad, y para comparar hicimos lo que teníamos por laboratorio, que es un micronizado. En experiencias anteriores hemos visto que cuanto menor es el tamaño del plástico que se incorpora, este se incorpora más fácilmente tanto al betún como a la mezcla. ¿Cuál es el problema del micronizado? Es que, como dijeron en la presentación anterior, cada etapa es plata. Cada etapa tiene un costo. Entonces, micronizar es un costo extra, una energía extra que se le agrega al producto. Por lo tanto, lo ideal sería usar los plásticos reciclados directamente, triturados en forma de escama, nada más que lavados, y ni siquiera en forma de pellets. lo que tiene el pellet, que es mejor para transportarlo, es mejor para incorporarlo en la obra. Entonces, veamos los resultados. En realidad, acá tenemos el asfalto base, el que se usaba normalmente en la planta, el modificado con el 3% de silo-bolsa, con baja densidad, el modificado con bidones de alta densidad, y también pusimos, para saber cómo se daba, un asfalto modificado comercialmente con polímeros. Encontramos lo que era de esperar. Las penetraciones bajaron, los puntos de ablandamiento aumentaron, los módulos aumentaron, pero lo importante de todo, y que podemos ver acá, es que la recuperación elástica torsional, que prácticamente no existe en los asfaltos comunes, digamos, empezó a ver algo, empezó a aumentar esa recuperación elástica. Entonces, como vemos acá, las penetraciones bajan, los puntos de ablandamiento suben, y tenemos una recuperación elástica que antes no existía. Fíjense, con respecto al CA30 que usamos, cómo aparece una recuperación elástica. También se hicieron los ensayos de viscosidad, y podemos decir que algunos cambiaron de flujo newtoniano a flujo no newtoniano, y que hubo un incremento de viscosidad de los asfaltos modificados, un aumento de la temperatura de mezclado y compactación. Si vemos los ensayos en el reómetro, como dije antes, tenemos aumentos en la rigidez y poco diferencia o casi igual los ángulos de fase. Si analizamos G por seno de delta o G dividido el seno de delta, vemos que no hay una mejora a la resistencia a la fatiga, pero sí hay una mejora sostenible a la resistencia al abollamiento, como se ha mencionado ya en este seminario varias veces. También se hizo Multiple Stress Creep and Recovery, y lo que es, digamos, no lo vamos a analizarlo en profundidad, sino lo que vamos a decir. El de acá arriba es el asfalto base, el que sigue es el control que se estaba usando, y el negrito de acá abajo, el AM3. Entonces, ¿qué vemos? Que los asfaltos modificados con plástico tienden a ir a ese valor de los asfaltos modificados comercialmente, con polímeros. Vamos a ver lo que pasa con los ensayos sobre las mezclas asfálticas. Entonces, recalcamos que la mezcla asfáltica de control era con CA30, no se cambió la dosificación de obra porque no quisimos interferir en lo que se estaba haciendo. Entonces, lo único que se cambia es con el mismo porcentaje el ligante asfáltico. Lo que podemos ver es que los porcentajes de vacío con la mezcla tomada de, digamos, de camión, nos dieron entre el 3 y el 5%, que es lo que pide la especificación argentina. Cumplía también con las densidades. Las estabilidades en algunos casos fueron un poquito mayores, en otros un poco menores, pero todas con buenas estabilidades y fluencias. El ensayo de resistencia conservada. En la presentación anterior dijeron que en algunos casos era bueno y en otros casos eran malos. La resistencia conservada en Argentina se hace por tracción indirecta, y lo que vemos acá, la muestra de control necesitaba aditivo. Se la preparó sin aditivo y no cumplía con el 80% de resistencia conservada que se pide en la Argentina. Pero los que tienen silo-bolsa por vía seca, húmeda y bidones por vía seca cumplieron totalmente, y que quedó un poquito por debajo fue bidones por vía húmeda. También se hicieron ensayos de módulo y de rueda cargada. Lo que podemos ver acá en esta curva maestra, aquí tenemos la temperatura, acá tenemos el módulo y acá tenemos la frecuencia, es que esta es la de control, la negrita. Las punteadas son por vía húmeda, las de línea llena son por vía seca. Vemos que a bajas temperaturas se rigidiza, también a altas temperaturas, por lo tanto, en nuestras zonas que las temperaturas son más elevadas, alrededor de 30 grados, podemos decir que es beneficioso porque va a tener menos deformaciones. Y eso se ve en el ensayo de rueda cargada, que todas cumplen con la especificación argentina, inclusive la de control, pero disminuyendo muchísimo la deformación cuando tenemos plástico. Vamos a ver entonces ahora los tramos experimentales. Vimos, digamos, qué pasó en el tiempo. Vimos algunas características superficiales, macrotextura, ahuellamiento. Apenas se terminó, se calaron testigos, y acá vemos el error que para nosotros, bueno, no se pudo hacer, es que los espesores fueron mucho menores a lo que nosotros pidieron, eso, y una falta de un equipo más pesado para compactar, por lo tanto tuvimos vacíos iniciales grandes. Las densidades logradas, obviamente, por vía seca son menores que por vía húmeda. ¿Qué tenemos acá? Acá tenemos macrotextura, a los 2 meses y 10 meses, huella interna, huella externa. Y acá tenemos los 5 tramos, silo-bolsa por vía seca, silo-bolsa por vía húmeda, bidones por vía seca, bidones por vía húmeda, tramo de control con el CA30. Los valores que nos dan prácticamente son los de cualquier mezcla asfáltica, y a los 10 meses lo que ha aumentado, digamos, disminuido la altura del parche de arena es muy poco. Y acá vemos el tramo, el de vía seca del silo-bolsa, que no está a los 10 meses, porque fue el que hubo que bachear porque estaba deteriorado. En cuanto a los ahuellamientos, tenemos los mismos tramos. En las líneas punteadas son los ahuellamientos iniciales, huella interna, huella externa. Y vemos que inicialmente hubo no llegó ni a 2 milímetros entre los 0 días y 2 meses. A los 10 meses estaba prácticamente lo mismo, y a los 22 meses tuvo un poquito más de deformación el tramo de control que los tramos con plástico, con lo cual nos ratifica el buen comportamiento a la deformación permanente de estos tramos. Y vemos que son 22 meses, pasaron 2 veranos, o sea, 2 periodos de altas temperaturas importantes, y siempre con cargas importantes durante todo el año. Veamos un poco de fotos, cómo nos veíamos a los 10 meses. Acá tenemos el silo-bolsa por vía húmeda, silo-bolsa por vía seca, bidones por vía húmeda, bidones por vía seca. Siempre del lado, digamos, derecho. Fíjense que acá ya a los 10 meses empezamos a ver por vía seca algún desprendimiento, y el que tenemos aquí es el tramo de control. A los 22 meses ya los tramos de por vía seca se hubo que fresarlos, y los que nos quedan para el seguimiento son los tramos por vía húmeda. Entonces, bidones, silo-bolsa, acá tenemos bidones vía húmeda a la izquierda y silo-bolsa por vía húmeda a la derecha, y este es el tramo de control. Los tramos están sin desprendimientos, sin problemas visuales, y lo que hay de alguna fisura, esta es una ruta bastante vieja que se la viene siempre reparando, o sea que son problemas tanto, fíjense que estas fisuras se han dado tanto en la parte de plástico como en la de control. Por último, entonces vamos a decir que el proyecto PASOS, Pavimentos Sostenibles, está enfocado en lo que se denomina People, Planet, Profits, o sea, la sustentabilidad. Mejor para la sociedad, mejores condiciones de circulación, que es lo que estamos buscando, reducir la cantidad de residuos plásticos en áreas urbanas, para el medio ambiente, reducir los residuos, menor consumo de energía durante el proceso constructivo, menos vertederos. Y economía, tenemos que tender a un diseño de pavimentos más duraderos con menos mantenimiento. Entonces, finalmente, las conclusiones que tenemos son las siguientes. Fue una experiencia muy enriquecedora, aleccionadora, ¿no? Dio mucho para saber lo que era lo bueno y qué era lo malo. Se avanzó en el conocimiento de los asfaltos modificados con plásticos reciclados en obra. Se evaluó la posibilidad de construir tramos en condiciones reales con mezclas asfálticas, con plásticos reciclados tanto por vía húmeda como por vía seca en obra, resultando que el proceso es factible de llevar a cabo y con equipamientos básicos. La planta era muy pequeña y los elementos que teníamos no eran para nada de última generación. Se destaca que este tipo de mezcla requiere mejores cuidados en el manejo de las temperaturas respecto a una convencional, o sea, verificamos lo que se viene diciendo en la bibliografía, no se debe sobrecalentar la mezcla, hay que evitar las pérdidas de temperatura durante el traslado y colocación, y previo al proceso de compactación para no tener un exceso de vacíos. Para nosotros sería conveniente trabajar con espesores mayores de 50 milímetros, y las mezclas por vía seca tendrían mejor comportamiento como bases y no como carpetas de rodamiento. Queda mucho por hacer, más ensayos de comportamiento, más experiencias constructivas. Nosotros teníamos planeado en el mes de abril hacer en la ciudad de Buenos Aires, nosotros estamos a 300 kilómetros de la ciudad de Buenos Aires, con una empresa con muchos mejores equipos, y vamos a dosificar especialmente la mezcla para estos usos, y por la pandemia tuvimos que suspenderlo. Queremos saber qué pasa con el RAP de estas mezclas, qué pasa con el RAP con plásticos, nuevas mezclas asfálticas, y también una evaluación del Life Cycle Assessment o también del Life Cycle Cost Analysis. O sea, esas dos cosas esas cosas son las que nos quedan por hacer, que nos queda pendiente. Y nuevamente, agradecer a todos por haberme escuchado, por haberme invitado, y estoy a disposición de ustedes para las preguntas.
Hola, Silvia. Bueno,
sí, no sé si puedo dejar de compartir.
Sí, por favor.
Que no lo veo por acá.
¿Así?
¿Ya dejé de compartir?
Sí, está bien. Bueno, nuevamente muchas gracias. Interesantísima y buenísima presentación.
Bueno, me alegro.
Yo te voy aquí a empezar a compartir unas preguntas, ¿ok?
Sí.
La primera viene del profesor Alberto Facchina. Felicitaciones por tu excelente presentación, Silvia. Solo para confirmar, ¿el ideal, según sus experiencias, sería la adición del polietileno micronizado y no en la forma del pellets, correcto?
Sí, o sea, lo que hemos visto, las experiencias de laboratorio, el micronizado, que pasa lo mismo también con el neumático fuera de uso. Cuanto más pequeño es el tamaño, la incorporación dentro del bitumen es mucho más factible, más fácil de hacer.
Ok, perfecto. Hay una otra pregunta también del Alberto. ¿Puedes mostrar más detalles, por favor, Silvia, sobre los resultados de resistencia conservada, daño por humedad, comentando sobre los valores para cada mezcla?
Todas las mezclas, o sea, el laboratorio cuando hacíamos las mezclas no preparadas en la planta asfáltica, en laboratorio todas dieron bien, daban por arriba del 90%. La mezcla esta que se hizo en la planta dio por vía húmeda por arriba del 80%, que es lo que pide nuestra especificación, y para baja densidad del polietileno, y para el polietileno de alta densidad por vía seca nos dio 72%, un poquito más bajo de lo pedido.
Ok, perfecto. Y te voy a hacer una pregunta para compartir. Bueno, interesante que nuestros vecinos estamos todos caminando en un mundo cada vez más sustentable, así por decir. Y me gustaría saber, en Argentina, ¿cómo es la financiación de los proyectos, bueno, para hacer investigaciones como esta? ¿Cómo está funcionando actualmente esto?
La financiación de los proyectos generalmente vienen a nivel nacional. O sea, uno presenta a la agencia los proyectos, algunos se aceptan, otros no se aceptan. Nosotros, principalmente en nuestro laboratorio, trabajamos mucho con las vialidades, tanto nacional como provincial, y tenemos propios producidos, entonces la parte de investigación la solventamos con esa parte. Y para la construcción del tramo específicamente, como dije antes, aportaron tanto YPF con el asfalto, la asociación digamos, que los que reciclaron pusieron el plástico, y las vialidades nos pusieron todo el resto de los materiales, los equipos y todas las cosas. Y todo el seguimiento, toda la parte de investigación, por supuesto, la puso la universidad.
Perfecto. Entonces, bastante en línea con que ya tenemos visto, ¿no? La cooperación es clave para un éxito de proyectos como este.
Exactamente. Y la que teníamos pensado era también con la ciudad de Buenos Aires y con otra empresa que estaba dispuesto también a poner todo el material y todas las cosas.
Sí, hay reciente una pregunta que yo creo que es algo que Carlos Alberto Tebit Filho nos hace. Si hay tramos experimentales planeados para ser construidos en corto plazo y otros plásticos van a ser usados.
En principio, el problema está en la viabilidad de tener el residuo. Entonces, en la Argentina en este momento las empresas que están reciclando plástico están reciclando polietileno. Entonces, uno tiene que, digamos, si alguien quiere usarlo a nivel industrial, tenemos que tener una industria que lo haga. El ACA, que nos da el plástico, en este momento usa casi el 90%, pero estaban dispuestos, si esto Vialidad Nacional lo acepta, lo pone en sus especificaciones, ellos pueden duplicar la planta. La planta es una planta que cuesta $8 millones, o sea, pero están dispuestos a hacerlo si realmente el mercado lo pide.
Sí, hay una pregunta ahora de Leni. Excelente, Silvia. En función de la mayor cantidad de plástico reciclado a ser introducida en la vía seca ser más favorable, ¿ustedes tienen cómo afirmar cuál sería la mejor alternativa, visto que, por ejemplo, en India, esta es la ruta más empleada?
La vía seca es la más fácil para que use cualquier planta. Se puede usar tanto por bastones como en una planta continua. Nosotros llegamos a poner con estudios de laboratorio hasta el 10%, pero se nos hacía como unas fibras, algo que no podíamos manejar ni compactar bien. Por eso empezamos a reducir la cantidad de plásticos incorporados y creo que lo óptimo habría que dosificar para cada caso, está entre el 2 y el 3%. Nosotros usamos, yo veía en Suiza, usan 6% de asfalto o bitumen. Nosotros usamos nada más entre 4,5 y 5. Entonces, creo que a lo mejor tiene que ser una mezcla que va a tener otras prestaciones. Entonces hay que ver qué prestaciones queremos para esa mezcla.
Perfecto. Bueno, Silvia, bueno, ya estamos en
tiempo.
Exactamente. Tenemos otras preguntas que le haremos llegar para que pueda entonces contestar. E, bueno, te voy a saludar ahora en portugués. Muito obrigado, Silvia. Bastante interessante a apresentação. Em nome aí do comitê de organização, de todo o grupo, agradecemos novamente a sua presença. Esperamos que também possamos tê-la aqui no Brasil em uma próxima oportunidade. E, bem, deixo agora a palavra para vocês, se quiser falar mais algumas últimas palavras para nós.
Agradezco, como dije antes, para mí ha sido un honor y siempre a disposición para colaborar con ustedes, para, como dijimos antes, trabajar en conjunto también en la parte de investigación. Obrigada.
De nada. Muito obrigado, Silvia. Bem, pessoal, agora acabamos de fechar a primeira palestra aí do nosso segundo bloco, do nosso terceiro dia do simpósio sobre plásticos reciclados no asfalto. Vamos agora para um pequeno intervalo para fazermos aqui a transição, tá bom? Aguardem, em poucos minutinhos estaremos com vocês aí. Até mais, muito obrigado.
Boa tarde, pessoal. Sejam bem-vindos à segunda apresentação desse segundo bloco, né, do nosso primeiro simpósio sobre plásticos reciclados no asfalto, no seu terceiro dia. É com prazer que eu dou as boas-vindas à doutora Raquel Moraes, uma pessoa querida, né, brasileira, que tem muito sucesso nos Estados Unidos. A doutora Raquel Moraes é professora assistente de pesquisa no National Center for Asphalt Technology, NCAT, obteve os títulos de PhD e MSc em Engenharia Civil e Ambiental na University of Wisconsin-Madison e o de BSc em Química Industrial, além de um MSc em Química Inorgânica na UFC. Como cientista treinada nos fundamentos das ciências materiais, sua pesquisa aborda temas na interface entre a química e a engenharia civil, com foco nas propriedades dos materiais, a partir de caracterizações geológicas e físico-químicas de ligantes, do envelhecimento oxidativo, da adesão, da compatibilidade entre materiais, da avaliação de dano por umidade e da modificação de ligantes. É um monte de coisa. Né? A doutora Raquel já atuou como pesquisadora principal associada em 17 projetos de pesquisa financiados pelo Estado e pela indústria no NCAT. Entre estes, a doutora Raquel liderou como pesquisadora principal 3 projetos sobre a incorporação de materiais poliméricos reciclados em ligantes via processo úmido, além de ter sido pesquisadora associada em outro projeto sobre o mesmo tópico. Publicou mais de 45 artigos em periódicos, anais de conferências, relatórios técnicos e fez cerca de 30 apresentações em conferências nacionais e internacionais. É membro dos comitês AKM20 e AKM40 do TRE, dos subcomitês ASTM de especificações de asfalto e de especificações de asfalto emulsificado, além de ser membro da APT e do ISAP. Então, sem mais delongas, eu passo a palavra para a nossa querida Raquel. Eu vou colocar meu microfone no mudo e vou passar os slides dela. Não é isso, Raquel?
Obrigada, Thiago. Boa tarde a todos. Primeiro, eu queria dizer que é um prazer, uma honra receber esse convite e participar com vocês desse seminário, mostrando um pouquinho do trabalho que a gente vem desenvolvendo aqui, nesse tópico que é tão atual. A apresentação foi feita em inglês, porque nós temos algumas pessoas que estão participando que com a língua invitation. Is a pleasure for me to be among such dear friends, and that we had the opportunity of being working together for so long. And today I'm going to be presenting a part of the study that we have been developing here in the United States at NCAT in partnership with the Western Research Institute in the utilization of recycled polyethylene incorporating asphalt binder using the wet process. So briefly, I would like to say that this work was performed in conjunction with the National Center for Asphalt Technology, NCAT, and the Western Research Institute. From the NCAT team, you have myself, you have Dr. Fan In, who will be also presenting after me. We have Dr. Nantran, and we have Mawazo Fortunatus, that he's a PhD candidate. And for the Western Research Institute team, we have JP that also presented on this symposium, I think, on Tuesday. And we have Michael that were the WRI team on this research. And this study was sponsored by the Plastic Industry Association here in the United States. So a little bit of introduction. I'm pretty sure that you have been seeing this over and over during this symposium, but I think it's a good way to introduce what I'm going to speak today. There are 2 processes where we can be incorporating the waste or recycled plastics into the asphalt pavement. One is the wet process, where basically we are adding the waste plastics as modifiers to the binder component, and the dry process, where we are adding the waste plastics directly into the mixture as either an aggregate replacement or a mixture fire. And today, this research will be focused on the wet process. When we use the wet process for incorporating evaluation of the recycled polyethylene in asphalt, we have some limitations and some challenges. And the most common issue that we face over and over in the laboratory is the phase separation between the two components. And this phase separation happens because the inherent incompatibility between the two components. And due to this incompatibility, the resulting mechanical properties of the modified binders are affected as well, and therefore the overall performance. And when we are trying to evaluate this type of material in the laboratory, what we have to consider is this component as a pseudo-binary system, where we have two components and the final performance of the material will be therefore dependent on the intrinsic characteristics of both material, as well as any chemical and physical interaction that occur between both components. So to have an overall picture of why this incompatibility process is so important and so visible in terms of the results and properties that we collect in the lab, we can see here the factors that play a role in the compatibility between the asphalt binder and the recycled plastics. We can see that solubility parameters, thermodynamics, and separation kinetics will dictate the overall microstructure of the asphalt pavements, of the asphalt waste plastic systems, and therefore we will see a significant effect on the modified properties of the resultant binder. The overall objective of this research was to characterize the chemical and the rheological properties of the asphalt binders that were modified with the recycled polyethylene, and also modified with a reactive elastomeric terpolymer that so forth will be called RET, that was used as a compatibilizer and performance enhancing of the recycled plastic in the asphalt binder. And here you can have, we have a flow chart showing the overall experimental design of this research. You can see that we initiated with only one base binder that was a neat PG58-28 binder, one and two SPS modified binders. And with these four components, we produce 9 different binders modified with recycled plastics, where 4 have the addition of the red additive, and 5, 4 without, and 5 with the red additive. And then we evaluate through the storage stability testing these 9 binders. And after this, the storage stability results, we select the binders that would be further evaluated in terms of rheology and chemical analysis. For rheological evaluation, we use SuperPave performance grading, delta TC, multiple stress creep and recover, the linear amplitude sweep, and the Glover parameter. And for the chemical analysis, we perform FTIR, infrared, differential scanning colorimetry, the SARA fractions of the asphalt, gel permeation chromatography, and we also did the MSCR tests on the portions of the cigar tube after the storage and stability testing. Here are the materials that we use in this study. As mentioned before, we have a neat PG58-28, and this binder was from Alberta, Canada. Then we have the recycled polyethylene samples that was supplied by Arema North American corporations. And here we have some 4 of physical chemical characterizations of this type of plastic: specific gravity, ash content, the melting temperature, and the most important, that is the polymer makeup. That is where this recycled plastic is a blend of low-density polyethylene and high-density polyethylene combined, 94% of low-density and 6% of high-density polyethylene. Then we have two ethylene-based RET, that is a terpolymer, that were used as compatibilizers to mitigate the phase separation between the recycled plastics and the asphalt binder. And for comparative purpose, in terms of performance, we have two SBS modified binders that were included in the study. One was formulated with 2.4% linear SPS, giving us a final PG of 64 minus 28. And the second one contains 4.2% of linear SPS polymer with a final PG of 70 minus 28. So let's go now to the discussion of the results. First, as mentioned before, our initial point was the storage stability test. Even though we know that this test is empirical, it is a very good initial test to screen among different modified binders, since we can clearly detect phase separation. So for this results here, we can see that we have the base binder modified with recycle. Can you see my mouse? No, because Tiago is controlling, right? Okay, so if you have any question on what I'm talking that you cannot capture what I'm trying to say, please let me know. So you see that on the four first samples, we have the base binder modified with the recycled plastic by itself in 4 different percentages, 2, 3, 4, and 5. And then we have the same blend of the binder with the recycled plastic modified with one type of terpolymer, and that is the RET1, and a different type of terpolymer, that is the RET2. And you can see that we use a criteria that is defined by the Georgia Department of Transportation that says that the difference between top and bottom samples after softening point cannot go over 10 degrees. And we can see that among all the binders that we evaluate, the samples that we evaluate, we only have 5 that pass the Georgia DOT requirements. And please keep in mind that we are not saying that by passing this test, we have a favorable blend. No, this was just the initial screening so we can move forward on the evaluation of these binders modified with the recycled plastics. And what we can see here is that by adding the recycled plastic, by adding the terpolymer to the recycled plastics blend, we decrease the severity of the phase separation of the recycled plastic with and the red terpolymer, we still have failure in the considering the storage stability parameter in accordance with the Georgia DOT specification. So, but when comparing the two terpolymer that were added as potential compatibilizers of the plastics with the binder, we can see that the terpolymer 2 additive was much more effective in mitigating the phase separation of the recycled polymers than in comparison to the terpolymer number 1. However, the terpolymer 2 is still failure to accommodate the highest percentage of recycled plastics that we try to evaluate. That was the 5%. As you can see, we fail when we have 5% of recycled plastics and the addition of the terpolymer number 2, meaning that this percentage of 5% of recycled plastics, in our experience with the projects that we have been working on, is way too much to be accommodated in the asphalt binder as modifier. And as you can see here on this picture, that is the green picture, trying to pause the mouse, but in the green picture, we have a UV microscope micrograph, and we can see like the very bright green parts that are indicated with the yellow arrow. These are isolated polymer coalescence that were caused by physical separation between the binder and the plastics. So, and this is for the blends with 5% of recycled polyethylene. So you see, you do not have dispersion of this material within the asphalt binder whatsoever. And then another way we decided to evaluate, and this was done at WRI, it was to, okay, we have the cigar tube storage stability test, and before we evaluate using the softening point. But now we want to see one thing that is not so empirical. Let's rely on the DSR to evaluate the properties, the rheological properties of the binder. So we perform the MSCR test on the top and bottom portions after the storage stability test. And here we can see, seen here, as in the graph illustrated on the left and the right side, you can see that the gray columns is top and the orange columns indicate the bottom samples. We can see that both the neat binder and the terp polymer modified binders had very similar JNR and percentage recovery values for the top and bottom samples. However, the binders that were modified with the recycled plastics and with the recycled plastics plus their terp polymer showed lower JNR and higher strain recovery between the top and bottom samples, which is an indication of a polymer separation. And also from these results, we can see that by adding the terp polymer to the binder modified with recycled plastics, we can decrease the severity of phase separation, but we cannot mitigate completely the problem. And here we have performance PG grade results, superphase PG grade results, standard PAV aging of 20 hours. And we have the high and low temperature continuous grade of the neat, the neat modified with plastic only, and the neat containing plastic only, and the terp polymers. And these are only the 5 binders that were screening previously using the softening point results after storage stability. You can see here that in comparison to the neat binder, we see an increase in the high temperature PG, sometimes by 2 or 3 grade bumps, depending on the percentage of the recycled plastics that is added. And on the low temperature end, we see no change on the performance grade in terms of the PG classification. And as you can see, the continuous to grade was very, very close. So the major effect of the recycled plastic is being in the stiffening of the binder that is indicated by the high temperature performance. And here we have so for performance comparison, 2 SBS modified binders, which had similar PG and delta TC as the recycled polyethylene blends, were also used for comparison purpose. And we can see that both the 2% and the 3% recycled plastic modified binders had a very significant lower JNR at 3.2 kilopascals and at 64 Celsius in comparison to the neat binder, which can be used as an indication of the effect of the recycled polyethylene on improving the rotative susceptibility in comparison of the asphalt binder, the base binder. Adding the recycled polyethylene and the terp polymer in combination even improved this susceptibility. And the important also to mention from this graph here that the RPE, that is the recycled polyethylene blends, plus the terp polymer blends had similar JNR values to the SPS modified binders. Continue on the evaluation of, Thiago, the previous one. In terms of the percentage recovery, we can see that the 2 and 3% binders modified with the recycled plastics had almost negligible percentage recovery at 3.2 stress level at 64 C. And on the other hand, the 3 recycled plastics polymodifying binders that contain the terp polymer used as compatibility compatibilizer had an improvement in the percentage recovered. And to mention what in comparison with the 70-22 binder that was modified with 4.2% SPS, that one was the one with the high elastic recovery due to the elastomeric nature of the additive. Here we have LAS results, linear amplitude sweep test, that was performed at 28C for all of the binders. On the left side, we have results of the number of cycles to failure when we apply 2.5% strain. And on the right side, we have the number of cycles to fail when we apply 5% of strain. We can see that regardless if it's 2.5 or 5% strain applied, the 2% and 3% are recycled plastic modified binders had similar number of cycle failure as the neat binder, which were way lower than the SBS modified binder. These results can be used to indicate that the usage of the waste plastic by itself for asphalt modification has no improvement on the fatigue resistance of the base binder. However, when the tar polymer was used as compatibilizer of the recycled plastic, we see an increase in the number of cycles to failure of the blend modified with the plastics. And when comparing the 70-28 binder, that is the SBS modified binder, and the one containing the 3% of the recycled plastics plus the tar polymer, we can also see that we outperform the SBS modified binder. Now we also evaluate the terms of the cracking susceptibility of these materials using the Glover-Roll parameter, which is a parameter that considers both the binder stiffness and embrittlement, and it is usually used as an indicative of binder's ductility and block cracking potential. We can see that by evaluating the results of the Glover-Roll parameters unaged, RTO4 aged, or PAV aged, that none of the binders modified with recycled plastics and with recycled plastics containing the tar polymer as compatibilizer exceed the criteria of 180 kilopascal for onset block cracking after 20 hours PAV. And therefore, based on this criteria, we can assume that these binders has a low probability of having premature block cracking in the field. However, careful should be we have to have a careful approach on that, because modified binders, we need to be careful when considering the limits that we have so far. And here we have the same Glover-Roll parameters that we show on that table, now plotted in a black space diagram, where we have complex modules on the y-axis and the phase angle on the x-axis at 15 Celsius and 0.05 rate per second. We can see that in comparison of the recycled polyethylene modified binders and the recycled plastics modified binders contain their tar polymers, we have similar stiffness, G star, but we have lower phase angle, which then results to the shifted, to the horizontal shifted of the data to the left of the diagram. I'm pointing here in the air, trying to to show on the screen. And again, it's important to highlight that none of the evaluated samples fell within the damage zone. They are indicated by the dashed and bold line. And on the left side, we have an aging index calculated considering the Glover-Roll parameter, considering the short-term aging binders and long-term aging binders. And we can see that both the recycled plastic binders, and the recycled plastic binders containing the terpolymer had very lower age index in terms of the global parameters in comparison to the neat binder, which can indicate a reduction in the aging susceptibility of these materials. And however, in comparison with the SPS binders, the SPS binders outperform the plastic modified binders in terms of the aging susceptibility. Then we start to evaluate the chemical characteristics of these binders. The first test was the infrared using ATR, attenuated total reflectance, where the material are evaluating the solid state without addition of solvent. And we can see here by the overlap of the lines of the neat binders and the neat binder modified with 3% of recycled polyethylene, we couldn't capture a significant difference between the neat and modified with recycled plastics. And then we move forward with the differential scanning calorimetry, the DSC results. And on here, what I'm going to be presenting from the results that we capture using the differential scanning calorimetry is the crystallization. And why this is so important? Well, we know that when we have materials that have a high wax content, we have very, very different rheological performance. And by adding the recycled plastic, we can be increasing the resin content, overall resin content on the binder, therefore increasing the content of wax and changing completely the rheology of the material. So we can see here that from the DSC results, when we have the neat binder by itself and the binder modified with the terpolymer only, we could detect any wax content or crystallizable fractions in the material. And then when we have the addition of the recycled plastics, we see an increase by 2%. Another important characteristic that we could capture using the DSC on this experiment was the melting temperature of the recycled plastic that we found happening at 114.7. I apologize for my background noise. Okay, Thiago, please. Then another chemical evaluation from this study was the SPRA fraction, the saturated aromatic resins and asphaltings that were captured in this study with the SPRA AD determinator, that is high performance chromatographic equipment that was developed by WRI. And in this specific way of separating the asphalt into its 4 SPRA these 3 types of aromatics, the resins, and 4 types of asphaltings. And here we have in these pictures some of the resulting precipitate that we obtained from each materials after evaluation with toluene as a solvent. We can see that on picture A, we have the neat binder that shows only 0.2% of material as being insoluble. Then we have the B, that is the binder modified with the terpolymer, which gives us 0.5% of insoluble materials. Then we have on the C, that is the binder modified with the recycled plastic, give us 14.2% of material as being insoluble. And lastly, the recycled plastic modified binder containing terpolymer, which give us 26.3% of material as insoluble. So from these SPRA results, as I mentioned previously on the picture, we have on the last columns the content of insoluble materials, where we can see that a significant portion of the blend that contain the recycled plastics is considered as insoluble. And then we can see the overall SPRA fractions for all of the 4 binders. But one thing that is important for us to see from these results is that these results could be used as an indication that the storage stability test alone does not directly represent the evaluation of the chemical compatibility of the polymer modifying binders. You remember that these samples were selected after initial screening of the storage stability test using the softening point, where we see that the binders passed the initial screening in accordance to Georgia DOT specification. But when we come to a more detailed or more intrinsic evaluation of the material, we can see that test does not cover everything. And we can, as we can see here, for the amount of insoluble materials that we have on the blends with the recycled plastics. And lastly, for the chemical analysis, we performed a gel permeation chromatography. One thing that is important to mention is the solvent that was used for this evaluation. The material, the recycled plastics, are not 100% soluble on it. And therefore, the collected results here are misleading because, oh, Camila, I'm way behind and I still have a lot of things to go. So what do I do? So do you want me to stop? Thiago? Go. Okay, she told me to go, so I go fast. Let me run. So as we can see over here, by the overall molecular size distribution curve, we can see that the modified binder are showing a lower overall molecular size distribution in comparison with the base binder, which we know that is unrealistic because of the size of the molecular weight of the polymer that is being added to the binder. So careful needs to be taken when we're doing analytical analysis of the material modified with recycled plastics, since the solvents that we use for evaluation cannot completely dissolve the recycled plastics. And then another evaluation that we made with this material was using the binding bond string test to evaluate compatibility with aggregate and also moisture susceptibility. And here's a schematic of the BBS, and since I'm running on time, I'm going to try to move fast for the results. First results that we have over here is the effect of the aging on the bond string of the recycled plastics. And we can see here we have POTS results that are collected with the BBS on Asia, that is original binding, and after PAV. And we can see that a higher POTS value or a higher bond strength is observed after oxidative aging. And one explanation for that is that the carboxylic acids that are present in the asphalt binder, and they are increased because they are products of oxidation, they are quite polar. Modifying binders are showing smaller dry bond strength. Then we evaluate the BBS after the samples using the BBS. We evaluate the samples after being submerged in a water bath for 48 hours, before and after aging. And we can see a significant decrease in the bond strength before and after aging, and considering moisture conditioning. Because, again, since the carboxylic acid groups are developed with oxidative, which they are favorable for the dry state, they are unfavorable when we consider moisture condition, because they can be removed very easily in the presence of water. And we see that this effect is more accentuated for the binders modified with the recycled plastic by itself. And then we also can see here, consider the overall loss of bond strength, meaning that is the ratio between before and after moisture condition. We can see that the samples containing the recycled polyethylene by itself are more susceptible to moisture damage after oxidative aging, in comparison with the samples that are modified with the terpolymer, because the samples that contain the terpolymer contain PPA, polyphosphoric acid, that is used as a catalyzer on this blend. And the PPA are known to react well with granite aggregates, therefore improving the overall moisture susceptibility of this type of blends. And we have here evaluation between the BBS results and the FTIR, where we can see that a higher loss of bond strength was observed for binders with higher carboxylic and sulfoxides area, as mentioned before, and this effect was way more accentuated for the binders that contain the recycled polyethylene by itself. So the overall conclusions of the experiment, I will go briefly, is that we can see that higher percentage of recycled polyethylene will not give us a passing criterion according to the Georgia Department of Transportation, and that the softening point testing results after storage stability can be misleading. So therefore, the MSCR test is a more reliable way of evaluation of polymer separation after the cigar tube storage stability. And we can see that with 2 and 3% of recycled plastic, we increase the stiffness of the binder overall, therefore the overall rotting resistance of the binder, but no effect is being detected as being positive regarding the low temperature cracking and fatigue cracking. And the DSC test was found to be a useful tool for evaluation of the recycled polymer modified binders, where we can detect melting temperature, glass transition, and the amount of crucible fractions. And lastly, what I would like to mention here, it was another very interesting study that we just finished, literally. And so on this study, it was not, the recycled plastic was not added to the binder. It was added to the mixture through the wet process. But we would like to evaluate that even though the recycled plastic is being added using the dry process, would this have any impact on the rheological properties of the binder? And that's what the study was aimed to achieve. So, and the hypothesis that we had is that the interaction existing between the asphalt binder and the recycled plastic can affect the overall performance of the mixture, even though it's used, it is constructed using the dry process. And the whole hypothesis would be that during mixing, the aggregate shear motion will result in the incorporation of the recycled plastic into the asphalt binder. And this degree of interaction, it is unknown. But if an interaction exists, it will result on change on the rheological properties of the binder that could be captured after the extraction and recovery. One concern that everyone has is regarding the solubility of the recycled plastic on solvents that are commonly capability of recovering the recycled plastic during the extraction recovery process. The obtaining binder, if an interaction exists, this obtaining binder will carry on it the chains after the interaction with the recycled plastics. And for this experiment, we use the exactly same recycled plastic that I have been discussed previously on the binder and chemical analysis. You can move forward, Jack. And here what we did, on this experiment, we have a control mix that was a PG58-28 binder that contains 20% wrap. And then we had a recycled polyethylene mix that contains a PG58-28 binder, 20% wrap, and 0.8% of recycled polyethylene. And from these two mix, we use structure and recover to obtain the binder, and from the resulting binder, we evaluate the material as unaged, RTF4, and long-term age on PAV, and I'm going to be discussing the results. Here we have a picture of the extraction recover process, and we can see that not all of the recycled plastic was melted or dissolved in the trichloroethylene that was used for the extraction. So we have high temperature continuous grade on the left side, and the G star over sign delta at 88C for both binders extracted from the control mix and the binder extracted from the mix containing the recycled plastic. And we can see by the results presented over here that we see improved resistance to rotting, because we see an increase in the binder stiffness as a result of our RPE modification, even though the recycled plastic was incorporated to the aggregate via wet process. We are seeing here change on the properties of the binder itself. And here we have fatigue. We also can see that we have a reduced fatigue resistance due to increase on the binder stiffness, a result of the recycled plastic incorporation. And in terms of the thermocracker resistance, we see a reduced thermocracker resistance as a result of the incorporation of the recycled polyethylene. We can see an increase in stiffness and a decrease in the relaxation properties evaluated in terms of the M value. And in terms of delta TC, we can see a double in the delta TC for the binder that was extracted from the mixture containing the recycled plastic in comparison with the binder extracted from the control mix without the recycled plastic, which shows that the binder extracted from the mix containing the waste polymer is much more susceptible to cracking after modification. And here we have an overall spectrum of the binder, of the performance grade results of the binder extracted from the control mix and the binder extracted from the mixture containing the recycled plastic. We can see a change in PG grade of 2 grade bumps from 76 to 88, and a decrease in the low temperature PG grade from -22 to -16. Therefore, we can conclude that the change in the rheological properties of the binder evaluated after extraction and recovery support the existence of an interaction between the recycled plastic and the basin binder, even though the incorporation of the plastic was through the dry process. And regardless the capability of recovering this recycled plastic during the extraction and recovery of the binder, the obtaining binder will always provide an insight of the degree of interaction with the recycled plastic. And with that, I conclude today's presentation, and sorry if I went over the time.
Raquel, muito obrigado pela apresentação. Sinceramente, foi tão legal que eu nem vi o tempo passando também. Eu acho que, como os tópicos são relacionados, da Raquel e do Fan, a gente vai deixar as perguntas no final, tá certo? Depois da apresentação do Fan, aí a gente passa as perguntas para a Raquel e para ele, tá certo? E aí a gente vai fazer uma pequena pausa agora e já voltamos com o Fan. Fiquem aí. Ok, pessoal, então sejam bem-vindos à terceira apresentação desse segundo bloco, do terceiro dia do nosso simpósio. É com prazer que a gente dá as boas-vindas ao Dr. Fan. Dr. Fan é professor assistente de pesquisa no National Center for Asphalt Technology, NCAT. Obteve os títulos de PhD e MSc em Engenharia Civil na Texas A&M University. A sua pesquisa foca em tópicos como projeto balanceado de misturas, caracterização avançada de materiais asfálticos e materiais de pavimentação sustentáveis. Serviu como principal pesquisador ou pesquisador associado em projetos de pesquisa avaliados em mais de 4 milhões de dólares. Ele é um engenheiro profissional registrado no estado do Texas também. Então, without further ado, Fan, I thank you very much for joining us today, and I think you can probably have the word now.
All right, thanks, Diego. Let me share my screen. If you can give me a... Okay, is this working? Okay. All right, thank you, Diego, for the introduction. And, thank you, everyone, for the great opportunity to be here, to be part of the program to talk about recycled plastic in asphalt. This is definitely a hot topic. I know we got lots of great presentation over the last two or 3 days. What I'm going to talk about today in this small presentation is kind of like a focus on the dry process. This is a proof of concept evaluation of adding recycled plastic in asphalt mixture. So this is a small experiment that we conducted here at NCAT to help us understand the process. And hopefully we can share some information with you all today. And hopefully you will find them useful and helpful. I'd say we already have enough discussion about, the difference between wet and dry process. Dr. Morris mentioned about, the wet process. We're adding recycled plastic into the asphalt binder. In that case, the typical dosage is 2 to 8% based on the literature review that we did for NAPA and AI. And for the wet process, typically we would prefer recycled plastic with low melting point because considering the production temperature of the asphalt mixture, those will be the plastic that can dissolve into the binder. On the other side, we have the dry process. It's a little bit different process where we're adding the recycled plastic into the mix. Right now, I don't think there's a good understanding about what kind of role do recycled plastic play in the mix. Do they play as aggregate replacement, mixture modifier, asphalt modifier, or combination of all the above? Based on the existing literature that we found out, the typical dosage for dry process is 0.2 to 1% by weight of aggregate. So there's a little bit difference between the wet process and dry process. And overall, dry process can accommodate more recycled plastic for use in the asphalt mixtures. I would say probably India is definitely the leading country on using the dry process of adding recycled plastics. Reportedly, they have almost 15 years of experience with this process. Right now, they have been using LDPE, HDPE, and PET in this type of application. The concept they are going after with the dry process is what they consider the plastic-coated aggregates. What that means is we're adding recycled plastic into the hot aggregates. Because of high temperature, the plastic gonna melt, gonna coat the surface of the aggregate. And by doing that, they can improve the mechanical property of the aggregate, including increase the toughness, abrasion resistance, and also those plastic films can, reduce the water absorption and the asphalt absorption when you do the mix design. And eventually, there's some literature or studies showing that the plastic-coated aggregate can improve mixture resistance to rutting, moisture damage, and fatigue damage. We talked with some of the contact over there. It seems that they have constructed over 1,500 miles of local roads with this technology. But the long-term performance data of those field projects remain to be determined. And about 7-8 years ago, the agency over there, the Indian Roads Congress, they established a specification that focused on the dry process of using recycled plastic in asphalt. So what happened to the mixture when we add the plastic into the mix using this dry process? By doing the literature review, we found out that many researchers use Marshall stability as the performance, measurement of the pavement performance. And those studies consistently show the conclusion that adding recycled plastic can increase the marshal stability. And there are some researchers then, based on this observation, they made the indication that, because of higher or increased marshal stability, adding recycled plastic can provide us with longer lasting payments. But we know this kind of conclusion may not be well supported because, first of all, based on the research that we have done over the last 20 years, 30 years with marshal stability, we know there's not a really good correlation between marshal stability and the rutting resistance in the field. Even if there's a good relationship over there, one thing that has not been considered is about the cracking performance. Right now in the US, cracking is a primary form of distress in asphalt pavements. So we definitely need to address those durability and cracking resistance of the mixture to be able to make our pavement last longer. There are quite a bit of research done to look at the stiffness and the rutting resistance, and they all show a positive impact from adding recycled plastic on those properties. But what's missing from the literature is, the distribution of the plastic. I mentioned this before. When we add the plastic into the mix, do they dissolve in the asphalt binder, or they stay outside the binder phase as kind of like a solid particles in the form of either aggregates, fiber, or mineral filler? I don't think there's a good understanding there. Also, we don't know the impact on the volumetric mix design. Because of very different specific gravity between the plastic and aggregate, it will affect those volumetric properties. And in the next few slides, I'm going to show some data that prove that discussion. I think what's the most important part is missing at this point is the cracking evaluation and moisture damage. Durability when we talk about the performance of asphalt pavements. But there's not quite lots of research on that perspective. And also we need to look into the surface friction and texture characteristic of asphalt pavements when we add recycled plastic into the mix. And finally, what kind of impact those plastics have on the pavement structure design. We talked with the French contractors who have experience with adding plastics using the dry process. They're saying that by doing the adding plastics, they can produce these high modulus plastic modified mixtures that can potentially reduce the pavement thickness. But there has not been comprehensive research to verify or to quantify those structural benefits. So with those questions in mind, we did a small study here at NCAT, try to evaluate or prove a concept type evaluation to understand the dry process. This is the same material, the post-consumer polyethylene material that Dr. Morris mentioned earlier in the study that we did for Plastic Industry Association. It's pretty much like LDPE with a little bit of contamination of the HDPE. The mix design we use is a very typical mix design that we have been using on the NCAT test track, a 9.5 millimeter surface mix with PT 5828 binder, 20% wrap content, which is about the average wrap content used in the United States. When we do the mixture testing, we look at the 3 different mixes, the control without the plastics, and then we did like 2 mixes with plastic. The first one is we took the control and we are adding 0.8% to plastics by weight of aggregates using the direct addition approach. And we keep the binder content the same, 5.5%. The second mix with plastic is pretty much the same as the first RPE modified mix, but the only difference is that we're adding additional more binder to make it a binder-rich mix so that it can provide a better cracking resistance and the durability. I know the dosage of plastic can be very confusing. In this case, we are talking about by weight of aggregates. But if you want to convert to the weight of binder, using total weights, it's a little bit less than 14%. But if you're using the new binder or the virgin binder, it's almost 17%. So it's definitely a much higher dosage as compared to the amount of plastic we can add in the wet process. The first thing we did is what we consider the aggregate coating trial. This is kind of like try to simulate the research finding reported from India. So what we did here in the lab is we preheat those aggregates overnight at very high temperature, like 340 to 370 degree Fahrenheit. I mean, that's the typical mixing temperature that we have been using. And then we're going to add those RPE pellets into the aggregate. But those plastic pellets were not preheated. So they were stored at room temperature, and they were just dropping into the bucket with hot aggregates. And then we're going to do a dry mixing without adding binder into it. And depending on different time, we look at what kind of interaction happened between the plastics and the aggregates. So very interestingly, this is what we found. So after we mixing the aggregate with the plastic, and we can separate the plastic particles from the batch. So right now I'm showing like 3 pictures. The one on the left is a relatively lower temperature, 340, and dry mixing 30 seconds. And then the one in the middle is a 370 degree Fahrenheit for the aggregate temperature, but we were mixing at 2 minutes. And finally, on the right side is the same temperature, but we extend the mixing time to 4 minutes. So the whole idea I want to show this picture is, as we can see here, for all these 3 mixing conditions that we tried in the lab, the plastics were deformed because of the shear reaction that applied to those plastics provided by the aggregate in the bucket mixture. But none of those mixing conditions was able to completely dissolve or melt the plastic so that it can provide the coating of the aggregate. So we were really not able to duplicate the aggregate coating experience that's reported by the researchers in India. We also look at additional sample. This is actually the real sample that we got from our contact in India. In this case, I would not call these like fully processed plastic. This is pretty much like a shredded plastic film. And then we did the same thing with dry mixing, but I don't know if it is clear from the picture on the screen right now. We were not able to see any aggregate coating in the lab trial environment. But the one thing I think we need to keep in mind is, all these experiments that we did here is in the lab. We need to ask ourselves the question, is the lab mixing procedure representative of what happened in the plant? When we talk about the plant operation, there's lots of factors we need to consider. Where the recycled plastic can be introduced. Are we introduced using the cold feed conveyor, or are we using the wrap conveyor or as around the wrap inlet into the drum plant? Depending on where we are introducing the recycled plastic, they're going to be exposed to very different thermal history inside the drum. And also like the interaction or the melting of the plastic depending on the aggregates, the temperature of the aggregate. So depending on where, once again, where in the drum inside the asphalt plant, the temperature of the aggregate can vary significantly, especially if we are producing mixes with wrap. Because of moisture content in the wrap, that can cause a significant reduction in the temperature of the aggregate. And that will affect the way the plastic interact with the aggregate and eventually affects the property of the mix. After the dry mixing experiment, so we look into the volumetric properties. So I'm showing the 3 mixes I mentioned earlier, and those are the air void at undesign based on the drum mix formula. So the whole point I want to make here is if we look at this air void number, for the control mix at undesign, we got 4.5% air void. But adding 0.8% polyethylene pellets into the mix reduced air void by 1%. I know like air void is still used by many agencies as, not only for mix design approval, but also for production acceptance. So if that's the case, we definitely need to be careful or be cautious about the impact on those volumetric properties provided by the recycled plastics. In terms of the other volumetric properties that are related to the durability, VMA and the VBE, those are important things that agency always looking to make sure that the mix is durable. In this case, if we look at the VMA, all these calculations in the middle part of the table, we are treating the plastic as aggregates. And then we adjust the GSB number of the combined aggregates. And then we do the calculation for VMA. In this case, the VMA also dropped by 1%. And if you do the difference between air void and VMA, we got the VBE. And then those 2 numbers are pretty much the same. So, which makes sense since we did not change any binder content in the mix. And, there was no binder absorption difference. So that's why they have very similar VBE numbers. But if we go to the other extreme, saying like, okay, let's assume all the plastic goes into the binder. In this case, the GSB of the aggregate remain unchanged. And then all the plastic going to be counted inside the binder. And then we do the calculation, we got a much higher VMA on the plastic modified mix. And then the same thing for VBE. So this result can be very misleading, since if we only look at those volumetric parameters, we may think, oh, we got enough binder in the mix, which should give us very good cracking and fatigue resistance. But those volumetric properties may not be fully reliable because it considers the plastic as part of the binder. In reality, that may not be the case. This is kind of like a picture of the gyratory specimen that we made in our lab, and we just using a wet saw cut into pieces and to just look at the cross section. As we can see here, there's lots of discrete plastic particles that stay outside the binder phase. So that we know, just looking at this picture, not 100% of the plastic goes into the binder. And the reality may be like the majority of the plastic may stay outside the binder. There's some research done by like Danish Road Institute. They use the same mixture slides and to look at the distribution of the plastics, and that can be a good way to further quantify the distribution of the plastic in the mixture phase. Dr. Morris mentioned about the challenge working with recycled plastic, especially in this case polyethylene, with some of the asphalt solvents. They are really not soluble. We look at the different solvent in one of the study. We work with WRI, and we realize this is something that we need to be careful when we do any binder extraction or recovery. But the interesting part is the same experiment that Dr. Morris mentioned before, that we can use solvent extraction in addition to the ignition oven to understand how much the plastic goes into the binder and how much of the plastic stay outside the binder. So the first thing we do is to do the extract and the recovery. And in that case, all the particles, the plastic particles that stay at the solid phase, going to be washed out by the solvent together with the aggregate. And then we can use the ignition oven to burn the extracted aggregate and the plastic residue. And then we can measure the weight change before and after. And based on that, we can estimate how much plastic goes into the binder, how much stay outside the binder. And in these small experiments, based on our calculation, we found out that only 10% of the plastic added into the mix was able to dissolve into the binder, while the other 90% remained in the mixture phase. So this definitely provides some information about what kind of roles do recycled plastic play in the dry process. And then we did a mixture evaluation to look at rotting resistant, moisture resistant using the Hamburg, ideal CT cracking, look at the intermediate temperature fatigue, look at the A-star to look at stiffness and viscoelasticity, and also using the AMPT cyclic fatigue test to look at the fatigue damage characteristics of the mix. And with A-star and the cyclic fatigue, we can do the performance prediction modeling using the FlexPave analysis. In terms of Hamburg analysis, I'm showing like the two approaches that we have been using. On the left side is kind of like the traditional way where we look at the total rod depth and the stripping inflection point. But then on the right side, we look at the alternative approach so that we can separate the rod depth caused by rutting versus rod depth caused by stripping. And in this case, we are using like a corrected rod depth and stripping number as the parameters. So now if we look at the results here, those are the same three mixes I mentioned before. I'm showing like two rutting parameters. For both parameters, a lower number indicates better rutting resistance. So keep that in mind. As we can see here, no matter which parameter we're looking at, the mixes with the plastics have a much lower corrected rod depth or total rod depth. That indicates the better rutting resistance, which agree with the high temperature binder rheological property that Dr. Morris mentioned before, and also agree with the research that has been published in the past. Another part we can get from the Hamburg analysis is the stripping, or the indication of the moisture resistance. In this case, the control mix showed the stripping in the Hamburg. Like there's some fine aggregate got stripped out, separated from the binder due to the adhesive failure, but we did not see that in the plastic modified mixes. So in this case, we're thinking that the plastic modified mix provide better resistance to moisture damage as compared to the control mix, at least when we do the evaluation using Hamburg. For the cracking evaluation, we look at ideal CT. This is probably one of the most popular cracking tests that has been used in the United States under the framework of balanced mix design. This is very similar to the way we run the TSR. It's an indirect tensile test. We apply the load on the vertical direction, and we measure the load versus displacement. When we do the TSR, we only look at the peak number. But in this case, we look at the entire load versus displacement data, and we consider the fracture energy, the post-peak slope, and by consider all these parameters, we calculate the final cracking index parameter called CT index. So a higher number indicates better cracking resistance at intermediate temperature. Now, if we look at the results, for the ideal CT, we look at the two aging conditions. We definitely recognize the importance of asphalt aging on the cracking evaluation. So we look at the short-term aging and long-term aging condition in the same test. Once again, like there are three mixes, the same mixes we have been using in this example. For each of the mix, the blue bar is the short-term aging and the orange bar is the long-term aging. So this one is a control. The second one is the plastics without changing the binder content. And then the one on the right side is a plastic modified mix at higher binder content. So very interestingly, from this data, we can tell that the two mixes on the left side did not show much difference at both aging conditions. But the one at higher binder content gave us a much higher CT index, which indicates better cracking or durability at the intermediate temperature. This is a little bit surprising to me because, we know like adding plastic gonna make the binder stiffer and, have reduced relaxation property, which should have a negative impact on the fatigue or the cracking resistance. I think one of the reasons that can cause this result is because the ideal CT test is highly dependent on the asphalt binder content. At this point, I'm still not 100% sure whether or not these tests can be capture the presence of plastic in the mix. I think definitely more research needs to be done on this perspective. When we look at the dynamic modulus test, we look at the E-star master curve, and we also look at the Glover roll parameter when plotted on the black space diagram. In this case, adding the plastic did not change the stiffness of the mix, which is also surprising to me, given the Hamburg data we showed before. But when we just look at the master curve, one thing we were not able to capture is the phase angle. But when we look at the data on the black space, it gives us a better indication of the mix behavior. So this is very similar to the way we look at the binder Glover roll parameter. We have stiffness on the y-axis and the phase angle on the horizontal axis. So not only we give an indication of the mixture stiffness, but also we can consider the brittleness of this mix. And in this case, if we look at the location of those two data points, the orange is with the plastics and the blue is a control. So as we can say, like the one with the plastic have a much lower phase angle when we test it in E-star, which indicates a little bit increased embrittlement. I'm showing the errors that we typically see with the impact of aging and rejuvenation. So in this case, there were not much increase on the stiffness, but it definitely adding plastic makes the mix a little bit more brittle. And that will affect the fatigue resistance when we look at cyclic fatigue data, as I will be showing in the next slides. And then finally, we look at the cyclic fatigue analysis. I know like we are running behind, so I don't want to spend too much time to talk about the theory behind these. But this is a test that uses a viscoelastic continuum damage model. And we got a C versus S curve, which gave a relationship between like the pseudo stiffness versus damage. And also we can look at a cracking index parameter called SAPP. In this case, a higher number indicates better fatigue resistance. Now getting into the results, when we look at the index parameter, as we can see very consistently that adding the recycled plastics, the mix has a much lower SAPP number, which indicates a reduced fatigue resistance. And we saw the same trend when we look at the pseudo stiffness versus damage. If we look at any given damage and we draw the line here, the one with the plastic has a much lower pseudo stiffness as compared to the control mix, which agrees with SAPP number indicating reduced fatigue resistance. And very interestingly, our engineers working in the lab running the test, he showed me this picture. As we can see here, there's some plastic particles that we can identify just based on visual observation that occurs at the cross-section at the failure point within the specimen. So it definitely affects the behavior of these mixes when we run the test. And finally, we use all these results to do the FlexPave analysis to look at the fatigue performance in the predict the fatigue performance in the pavement structure. In this case, we were looking at the bottom-up fatigue cracking as kind of like the main mode of distress in evaluation. When we do the prediction, we fix the pavement structure for the control section. When we adjusting the thickness of the plastic-modified mix section, try to match the equivalent damage due to bottom-up fatigue cracking. Based on our simulation research and result, we found out that we need like a 7-inch of the plastic-modified mix to be able to provide the same damage resistance as the control mix using only 5-inch hot mix asphalt. This is related to the reduced fatigue resistance of the plastic modified mix, so that we need to increase the thickness so that we can reduce the strength at the bottom of the asphalt layer so that it can improve the fatigue resistance. Finally, a quick summary of what we found so far. We look into the aggregate coating approach, but we were not able to duplicate what has been reported in literature. When we look at adding 0.8% of recycled plastic, we realize it definitely reduced the air void. This is something for mix designers we need to be cautious. And also, when we report those VMA and the VBE results, we need to be very careful because depending on how what kind of GSB number we are using, the VMA and the VBE results may not be entirely reliable. In terms of rotting resistance, we saw improvement on the high temperature behavior, which is a positive sign. We did not see any significant impact on ideal CT. But when we look at the AMPT cyclic fatigue and also the FlexPave predictions using the bottom-up fatigue damage model, we realize adding plastic can have a negative impact. And also, these similar research findings have been reported earlier this year at TRB. There's a workshop. There's a presentation by Cola Solutions. They also reported their result on the dry process, which agree with the finding we have here. Once again, this is a very small scale proof of concept type evaluation, but here at NCAT, our research team, we learned a lot from this. But moving forward, I think more research is definitely needed. I think Dr. Richard Willis mentioned this morning about the NCHRP project, and that can be a good research to look further into the dry process. With that, I definitely appreciate the opportunity. Hopefully you found this helpful and useful, and I will turn the floor back to Tiago and see if there's any questions.
Thank you very much, Fan. Very interesting presentation. You guys are doing a terrific job at NCAT on this topic, and it's very good for us to have this connection with you. I hope this is the first time that we have this connection and that you guys can interact with our Brazilian community here in this topic and in other topics. Okay. What happens here is that Raquel was answering the questions, and her answers are there on YouTube. And I don't see any questions so far here. Let me see. Actually, there's a question here. So Camila says, very nice presentation, Fan. And by the way, there were many other comments that congratulated Raquel for the very nice presentation that she gave. And the same here to you. And Camila says that, and she asks, do you think the need for higher mixing time, when using RPE might make the process too expensive and maybe not sustainable due to the energy consumption?
Well, I think that's definitely a very good question, and I agree. I mean, I think that can be a concern. We talk with some of the contractors here in the U.S., they also express the same concern. If we really need to increase the temperature to make sure that the plastic can melt or more plastic can go into the binder with the shear action provided inside the drum, then that's going to be a cost because of energy consumption and also may not be good from the environmental benefit, like a perspective. There's some same discussion about using recycled, wrap or shingles, but I think we are talking a much higher temperature as compared to those recycled asphalt material. This is something that definitely need to look into. I know using recycled plastic have, some, sustainable benefit, but at the same time, we need to consider the performance, the cost, and some other factors. This is a full picture that we just cannot, overlook one part of that. But I agree with what Camila suggested.
Very good. Adalberto also congratulates you for the presentation and asks, to what do you attribute the unfavorable results in terms of fatigue resistance after adding PE to the mixture?
Tiago, I'm not sure. I think I lost you for a few seconds and I missed the first part of the question. I heard like a fatigue resistance.
Okay, let me repeat it for you. He asked, to what do you attribute the unfavorable results, the bad results, in terms of fatigue resistance after adding PE to the mixture?
Okay. Yeah, I think, I think there are two parts that can, play a role here when we talk about the reduced fatigue resistance. One is the overall stiffening impact. I think Raquel showed the result on the binder side that shows, the plastic definitely makes the binder, the liquid, stiffer. At the same time, what we saw on the cyclic fatigue data is, before we run the damage mode, we look at, the non-damage relaxation property. And we realize adding plastics to have a detrimental impact on the relaxation property. So, the overall stiffening impact and, the relaxation property, those are the two factors, I think, causing the reduction in the fatigue resistance. This is something we definitely need to be very careful. I know here in the US, we're struggling with fatigue cracking, thermal cracking all the time. So this is something we need to, provide mix design modification to improve this performance if we want to use recycled plastics.
Okay, thanks. And the last question from Renee Leite. She also congratulates you, of course, and she says, she asks, the fact of bad homogeneity of RPE in dry mix can explain in part the bad performance in CT ideal index and damage as of cyclic test.
Yeah, I agree. That's a good point. It's, that's why the state agencies here in the US, they prefer the wet process and the dry process because on the wet process, they can better control the homogeneity or the quality of the mix. But when we do the dry process, we don't have 100% control on the distribution or the homogeneity. So if we have, plastic not uniformly distributed, and the way we run the lab test, either ideal CT or cyclic fatigue, there might be some localized agglomeration of the plastic that can give different results depending on where we're testing and where the failure started. So, that's always, an issue when we look at the connection between lab testing and field performance. So especially for the dry process, not only plastics, rubber, fibers, all those have the same issue. The homogeneity need to be considered. And I really don't know, how we can, accurately or, comprehensively evaluate that based on lab testing. So that's why I feel like a field performance evaluation by doing the demonstration project is much needed to provide the performance data to our industry.
Okay, awesome. And I think with that, we'll conclude the question and answer section. And again, I thank you very much for your availability. I know that the agendas are very busy these days, and the fact that you guys spend some time with us sharing your knowledge and probably opening a connection for further studies and joint efforts is very good, and we are very thankful to both of you, okay?
All right, thank you very much.
Thank you, Raquel. So I think, eu acho que agora a gente, Adalberto, a gente dá uma pausa ou eu passo para você concluir?
Já vamos passar para a sessão de encerramento, Thiago.
Tá, então obrigado, eu concluo aqui a minha fala e passo para você.
Perfeito. Vamos, então, já emendando, certo? Com a finalização das palestras para a nossa sessão de encerramento do nosso evento. Foi uma grande jornada, né? Muitos palestrantes, especialmente hoje, né? Com 5 palestrantes internacionais. Então, eu gostaria de pedir para os componentes do nosso comitê organizador agora abrirem as câmeras, né? Para nós fazermos cada um uma fala final para concluir o nosso evento, né? E eu quero inicialmente fazer um agradecimento geral, né? E depois já passo a palavra para os demais e aí depois eu encerro, tá? Eu preparei uma mensagem para o final também curtinha, mas inicialmente eu quero então agradecer primeiramente aos colegas que estão aqui na tela, né? A professora Camila Vasconcelos. Acho que a Camila está com um probleminha lá na conexão. Vou pedir só para vocês abrirem a câmera e falarem um oi para poderem aparecer no YouTube. Embora vocês vão falar depois, obviamente, mas eu queria destacar, então, a grande contribuição de todos, né, no sentido de ter nos ajudado. Foi um grande trabalho conjunto, né, a organização desse simpósio. Então, a professora Camila Vasconcelos, da Escola Politécnica, se puder abrir o microfone e falar um oi só para aparecer.
Oi, não sei se vocês me ouvem.
Pronto. Então, também agradecer ao professor Tiago Aragão, da Federal do Rio de Janeiro.
Olá.
Nosso amigo Rafael, da Creighton Polymers.
Olá, pessoal.
E também a nossa querida Leni Leite. Então,
Oi.
Muito bem. Eu quero fazer inicialmente esses agradecimentos, então, especialmente ao comitê organizador. Não estamos aqui com o Luiz Alberto, do Centro de Pesquisa da Petrobras, mas vou deixar aqui também registrado o agradecimento do grupo, a todo o apoio dele também. E depois disso, preciso agradecer muito ao nosso técnico de informática, o Carlos, que trabalhou arduamente e possibilitou toda essa nossa transmissão suave, tranquila, né? Apesar de todos os desafios que nós tivemos aqui nos bastidores e que aparentemente ninguém percebeu aí no YouTube, felizmente, né? Mas tudo isso que nós conseguimos transmitir pelo YouTube foi suave dessa maneira, com essa transmissão suave dessa maneira, por conta de um trabalho muito grande, muito bem feito do nosso técnico Carlos, que é parte aqui da nossa equipe da Escola de Engenharia de São Carlos. Agradecer também o apoio valioso dos nossos alunos, né, que sempre estão dispostos a nos apoiar e que proporcionam um auxílio, uma ajuda fundamental para que muitos detalhes dos nossos eventos aconteçam, né? Em particular ao Matheus, que é representante dos alunos do programa de pós-graduação de Engenharia de Transportes aqui da EESC, e em nome dele eu agradeço, então, a todos os demais que nos ajudaram com o compartilhamento das perguntas do YouTube aqui para a nossa sala do Meet, e também os que ficaram responsáveis aí por proteger o YouTube contra eventuais invasores, né? Então, nos ajudaram bastante, eles não aparecem, né, mas eles fizeram um trabalho muito bacana nos bastidores também, né? E, por fim, agradecer aos todas as empresas que nos apoiaram, né? Que também, então, contribuíram bastante com a divulgação do nosso evento, então, nosso agradecimento também a todos. E aí eu passo, então, agora a palavra para os demais componentes do comitê organizador para darem uma mensagem final. Vamos começar, ladies first, pode ser? Começamos com a Leni, pode ser? Abre seu microfone, tá?
Pode ser sim. Então, eu acho que o evento foi muito proveitoso. Eu acho que os espectadores, nestes dias, aumentaram bastante o conhecimento sobre o uso de plásticos reciclados no asfalto. Foram palestras bem esclarecedoras do que está sendo feito no Brasil e no mundo, tanto do ponto de vista técnico, como também da disponibilidade de plástico reciclado aqui no Brasil, destacando a palestra do César e da Biplast. Quero ressaltar também a participação dos alunos, mostrando a preocupação das universidades brasileiras pela utilização desse plástico reciclado, que, ao final de tudo, vai contaminar nossos oceanos, os nossos rios e o solo. Eu acho que é o ponto de partida para a gente iniciar um estudo nessa área, né? As universidades brasileiras capitaneando isso, de alguma maneira, fazendo, combinando que cada um, qual a sua tarefa de cada um, para não haver repetições, e as entidades que formam todo esse ciclo devem serem convidadas. Vamos ter que se preparar para isso. Parabéns pela organização, Camila, Adalberto, Rafael, que tiveram assim à frente o tempo todo, dia a dia, sobre isso. Eu acompanhei pelo WhatsApp e foi um mesmo sucesso. Parabéns.
E a gente agradece muito você, Leni, que tendo você por perto, a gente fica sempre muito mais feliz e muito bem amparada tecnicamente e com entusiasmo seu de sempre. Então, foi muito legal ter trabalhado com você mais uma vez, né? E agora num evento desses, né? Obrigado, então. Aí passo agora para a professora Camila Vasconcelos, da Escola Politécnica.
Bom, eu queria só brevemente agradecer o empenho de todos, né, a audiência, a todos os palestrantes que fizeram esse evento acontecer. O que eu achei talvez mais bacana foi realmente uma união de esforços, não só de instituições, acho que o Rafael tinha comentado isso antes, uma união de pessoas, né, em prol de um tema que afeta todo mundo no final. E essa parceria das universidades, né, com as associações, com a indústria, né, entender qual é o problema que a gente está tentando resolver, impactar de uma forma positiva com os nossos estudos, né, com as coisas que são desenvolvidas dentro da universidade, impactar de uma forma positiva o ambiente que a gente vive. Então, eu agradeço, eu acho que eu aprendi muito durante esses 3 dias, com essa troca de informações. Fiquei muito feliz, acho que a gente tem muito para avançar, e vamos avançar, né? Então, agradeço a todos, espero que em breve a gente esteja fazendo um novo evento, né, trazendo mais novidades, e talvez agora bem mais das... Tá bom? Um abraço a todos, e obrigada.
Perfeito, Camila, muito obrigado a você também por todo o apoio ao nosso comitê organizador. Agora passo para o Rafael, da Creighton Polymers.
Pessoal, então, muito obrigado novamente a presença de todos quem estava participando, né, por meio do YouTube, e também um agradecimento especial a todos os palestrantes, né, foi um evento, um simpósio global, né, unindo aí vários países, e gostaria de agradecer também em nome da Kraton o convite para podermos aqui ajudar, né, auxiliar nessa coorganização, e como pessoa também, como CPF, eu acho que esse simpósio foi uma união de CPFs, né, de várias pessoas em comum, que a gente trouxe de tabela as entidades que representamos para poder, então, fazer e dar um primeiro passo em conjunto para podermos aí construir um futuro mais sustentável. Acreditamos que a sustentabilidade e a performance, elas trabalham e andam lado a lado, que eu acho que esse foi uma das mensagens aí principais que eu levo, que a gente vê que está bastante alinhado. Então, aí, juntando a indústria, a academia e órgãos aí governamentais, né? Muito obrigado pelo convite, agradeço novamente aí a todos que estão presentes, é isso aí, boa noite.
Obrigado, então, mais uma vez, Rafael. Agora é o professor Tiago, da Federal do Rio de Janeiro, por favor.
Obrigado, professor Adalberto. É um prazer estar aqui junto de vocês. Agradeço o convite que me fizeram para fazer parte desse comitê organizador. Tenho que dar os créditos a vocês, né, que fizeram muito mais para esse evento do que eu, para ele acontecer, mas também foi um prazer para mim participar junto de vocês. Eu estava escutando a fala do Rafael e pensei, eu acho que esse tipo de assunto tem que ser explorado de maneira conjunta, porque toda a sociedade vai se beneficiar com ele, realmente, né? É um interesse público, né? A gente, enquanto pesquisadores, enquanto pessoas que têm condição de viabilizar o uso de novos produtos, novos processos, né? Eu acho que nós temos a obrigação de trabalhar nesse tipo de abordagem que vai ter um ganho social muito grande, né? A gente precisa envolver diferentes atores também, não só a academia, não só as empresas, mas também agentes do governo, enfim, catadores, né? Enfim, a gente precisa ter um melhor processo de coleta seletiva. Então, eu acho que é uma coisa que precisa realmente envolver várias habilidades, várias pessoas, para ter um ganho, de fato, grande para a nossa sociedade, tá? Nós estamos, lá na COP especificamente, já tendo alguns alunos trabalhando nesse tópico, né? A Leni, o Luiz Alberto e eu, a gente está juntos numa orientação de 2 alunos, e a gente sabe que outras universidades também já estão investindo em estudos nisso. Então, é um tópico que realmente nos interessa e eu acho que é pronto, né? Não dá para esperar mais. Então, obrigado pelo convite, estaremos juntos nas próximas oportunidades.
Perfeito, professor Tiago. Nós agradecemos muito sua participação também. E, bom, com isso, então, eu vou finalizar a minha fala só com mais algumas palavras e lembrando, né, que um agradecimento bastante importante, agora geral, né, a todos os palestrantes e também ao público que nos acompanhou ao longo dessa jornada de 3 dias. Eu sempre digo que um grande evento se faz com grandes palestrantes e um grande público, né, um público de qualidade. E palestrantes de qualidade, acho que nós tivemos muito sucesso graças a essa combinação desses 2 aspectos, né? E então nós tivemos aí um evento bastante diversificado, com a participação, né, de muitos especialistas, tanto brasileiros quanto estrangeiros, em diversas áreas, mostrando então que acho que um dos grandes aspectos que ficou bastante claro é que o desafio da incorporação dos plásticos aos asfaltos é um desafio multidisciplinar, né? Então, esse foi o primeiro evento que nós realizamos tratando desse tema aqui no Brasil, e a gente espera que essas reflexões todas que nós podemos fazer acerca desse tema durante o nosso evento possam fomentar novas pesquisas e novas ações, no sentido, então, de aprimorar a técnica da incorporação de plásticos ao asfalto. Um aspecto que eu quero destacar aqui é uma técnica, essa técnica que nós estudamos, que nós discutimos aqui, ela pode, então, se integrar a outras iniciativas que já estão em andamento, no sentido de diminuir o impacto negativo dos plásticos descartados no meio ambiente. Porém, o nosso evento também tem uma mensagem bastante direta, né? Nós temos, sim, uma técnica muito promissora, né? Porém, é importante deixar claro que ninguém deve entender que já deve ser empregada indiscriminadamente. Tá? Nós temos fazer mais estudos, né, aprofundar os estudos, para que a gente possa buscar soluções para algumas dúvidas ainda existentes. E, nesse aspecto, nós temos, então, certeza que as nossas universidades e os diversos agentes envolvidos com a reciclagem dos plásticos saberão dar essas respostas adequadas para a nossa sociedade. Bom, com isso nós terminamos, então, né, esse evento que foi tão bem sucedido. Esperamos, então, encontrar todos novamente num próximo evento futuro, né? E agradeço, então, a todos novamente, e até a próxima. Um abraço a todos, então.